the presentation. I will do a quick presentation of the CHEERS project and focus then on the introduction of this webinar. So if we move on. What is CHEERS? Just for the people who don't know, CHEERS means Chinese European Emission Reducing Solution. This is it is an R&D international program to reduce greenhouse gas. So for that, there was a consortium set up of 8 members, some of Europe, some of China, to tackle this issue. On the Europe side, so we have the partners SINTEF, TotalEnergies, IFPEN, Bellona, and Silesian University. And on the Chinese side, we have Dongfang Boiler Group, part of the EC company, Tsinghua University, and Zhejiang University. So the objective of this consortium, sorry, is to demonstrate a new second generation CCS technology to make it passing from a TRL 4 to 7. TRL means technology readiness level. And the 2 main deliverables will be to design, build, and operate a chemical looping combustion of 3 MW and validate this technology with petcoke and lignite feedstock. The second deliverable will be to do a techno-economic assessment of an industrial scale CLC CCS unit. So just to let everybody know what is the CLC. CLC is a combustion technology with inherent CO2 capture with energy efficiency. That means, so in this technology, we are in front of 2 reactors, sorry. On the left part, you see the, sorry, I have to drink a bit. You have the air reactor, sorry, on the left side, where you inject air and you put air in contact with some oxygen carrier. Oxygen carrier is like the hemoglobin in the blood. It will fix the oxygen by getting oxidized with the oxygen. And the nitrogen from the air is passing through the reactor and go back to the stack. This oxygen carrier is just then sent into a combustion chamber where the combustion can react with the oxygen bring by the oxygen carrier. From this reaction, you bring heat that can generate steam or furthermore generate electricity if needed. But from this combustion, as you don't have any nitrogen, you will have a flue gas made of 96% CO2 in fact. So in this technology, you don't need an ISU air separation unit. You don't need neither an amide unit to capture the CO2. And this unit is mainly designed for solid feedstock, like mainly petcoke, pitch, or coal. But we can have also possible biomass, waste, or gas feed. For the CHEERS project, like many projects, we are divided in a different work package. So if you see the middle line, we have work package 2, was led by IFP and THU on the process design. And then we jump to work package 4 for the feed part. And this is the part we will speak today. And part of this work package is also one of the industrialization study for the CO2 treatment. And then after the work package 4, we jump to work package 6, which is the EPC, engineering, procurement, and construction of the unit. And parallel to these 3 work package, we have work package 3, we got leading by SINTEF on the oxygen carrier development, and work package 5, which is more on the industrialization of the unit, by modeling industrial scale units and doing a technical economic assessment. Work package 1 is done by SINTEF for the coordination of the project. And as Todd explained, the work package 7 for the communication and dissemination done by Bellona. So this project started in 2017. And in 2018 and 19, it was more the design part. In 2021, we had the feed part with this work package, number 4. 22 will be dedicated to the EPC. And 23 will be dedicated to the test on this unit. So for today, we will speak mainly about work package 4 and the feed preparation. This is to ensure an optimal integration into Dongfang boiler site. Then we will see the feed achievement, how we pass from PDP to feed with all the different challenges we faces. And then we jump to EPC preparation. And then we speak about one of the CLC industrialization study, mainly focusing on CO2 treatment. And then we go to conclusion. So now I will pass the floor to Aoling Zhang, who will speak to you about feed preparation.
Okay, thanks, Vincent. Yes, please take a short break and drink more water. Okay, so dear audiences, this is Aoling Zhang from TotalEnergies, China, taking the role as site coordinator. So please allow me to bring you some debriefings about feed preparation or pre-feed activities, as Vincent described. So next page, please, Vincent. Yes, so I would develop many from 4 aspects, including construction strategy change, which took place several months ago before closing the PDP dossier in 2019 after careful studies, and then site survey activities, which were organized again in purpose to better understand the site, especially for utility adequacy checks, and then safety management, which is a paramount priority among all TotalEnergies projects. So last but not least is a introduction about cover tender activities for feed in brief. Okay, next slide. So yeah, to begin with, about the construction strategy change, it was surely a decision with vast influences. As you can see in the models, CHEERS was planning to do a retrofit on existing circulating fluid bed boiler, we call it the CFB, by reusing the blue components in the left picture. However, as the design went deeper, the team came to realize that the retrofit plan seems not evident, even impossible to some extent. Not to mention those constraints placed on R&D flexibilities because of retrofit. There are far more new items as shown in brown to be added, which could bring huge actual nodes to existing steel structure. So if we stuck to retrofit, in order to enhance the steel structure, we were supposed, as told, to remove all existing components inside, put new steel columns and beams in, and feed back all equipment, new or old, in the end. This could be a tremendous work and in extremely high actual cost. Finally, after weighing all pros and cons in a comprehensive manner by using SWOT, we took a grassroots construction strategy in the end. So although this would bring unavoidable rework for the PDP dossier and feed cover tender preparations. Okay, next slide, please, Vincent. So also due to above change from retrofit to grassroots, as I explained, before starting feed, the feed team had to go back to the site again and reorganize a new round of site surveys. The objective was to double check the adequacy of existing utilities and other possible limits, For example, we were informed there was only 800 kilowatts power capacity altogether in EPC site, and already 250 kilowatts was taken by other facilities like fuel grinder or cooling water system. So in this way, we could only have about 550 kilowatts left for new add-ins. This can be in shortage, yeah, because we expect to have about 700 kilowatts from PDP results. Surely, in between, some correlation would be needed for this issue. At the same time, on the other hand, also thanks to the survey, we also learned that DBC, they just established a brand new DCS room, as you can see in the upper right picture. It's a brand new, yes, thanks Vincent. And to save cost, we then started to persuade DBC to spell a dedicated workstation for CHEERS project only. This can be a greater promotion for EPC demonstration, CLC demonstration as well. So next one. Yes, regarding safety management, FEED team had attached super high attention as always. Clear references for both process safety and operational safety were well defined at the moment. To better input FEED studies, we also updated the pre-FEED hazard report while analyzing 83 scenarios and concluding 35 recommendations. So here we got a sample worksheet in the middle, as you can see. So for instance, during site surveys in the EPC, we noticed that DBC already had a well-settled procedure for solid waste handling. Therefore, CHEERS could rely on the existing procedure to deal with solid waste. And we also suggested other process safety workshops like HAZOP or LOPA for both FEED and EPC, although it could be DBC's decision, Dongfang board decision, how to organize EPC relevant ones. Okay, next one. Yes, my last slide is about corporate tenders TotalEnergies had organized to prepare FEED. To be honest, this is a process beyond communication. If you remember well, the pandemic just broke out, and it was right in the moment the team was trying to convert CLC concepts to engineering practices from the best. So it's quite worthwhile to mentioning that lots of FEED tenders quit themselves even in the first rounds. Some of them claimed uncertainty about this research background. Some of them had fears about construction strategies change, and some of them even expressed worries for pandemic impacts. It was sure not an easy period, but the other way around, this rightly proves the hardship and the value of a final success of the FEED in the end. So to save time, I will stop here, and then my colleague Madi share you more stories about FEED and its achievements in the coming months. Thank you all. Yes, Madi.
Thank you, Aoling. Good morning, good afternoon in China. My name is Mahdi Yazdanpana, and I was working at R&D in charge of CHEERS project till this September. We actually were working on the FEED together with Aoling and Guillermo Nicola, who is not present today, and I would like to present briefly the outcomes of these phases of the project that we can see from the next slide. Actually, FEED, as you already saw, stands for the front-end engineering design, and that's the major engineering step before start of construction. Therefore, still in this phase, we are talking about a design which is on paper, and it converts, especially in case of a demonstration project like CHEERS, conceptual and R&D design into a conventional engineering design, which will be used as a basis for construction of the plant. Therefore, we convert something which has a notion of R&D and a notion of engineering to something which is understandable by different companies for construction of a plant. And modifications and improvement are still possible in this phase, thanks to the fact that even if you're talking about engineering, but that's still on paper. Therefore, we don't have materials, and thanks to that, the impact of modifications are still measurable and controllable. An important point about this phase is the fact that we are supposed to use standards, norms, and regulations on top of the simulation and modelings for design. Therefore, design should respect lots of different constraints in addition to what we have from the previous phases. And at the end of this phase, we prepare a decision support package, which will be used for the final investment decision. In this package, we should show that the concept works, that the engineering level is enough to start the EPC phase, and the costs of and the planning are well mastered based on the what we have got from this phase. As Auling mentioned, we did a call for tender for the FEED phase, and it was Worley who won this project thanks to his excellent answer to the call for tender. And they mobilized 2 offices, mainly in Europe, in Belgium, and in China. In next slide, we will see that how this was organized generally. As you can see in left-hand side, we have the team mobilized within the engineering company Worley. The teams were mainly located in 2 offices in Europe, where we had some disciplines like process, mechanical, analysis, and safety. And in Chinese office that we had instrumentation, electrical, piping, structure, and civil. The reason to choose this distribution was a proximity and to ensure a good exchange. And in some disciplines, we needed to respect local norms and regulation in China. For example, the structure or civil, on top of what we have from conventional engineering, we must respect the local regulations. Therefore, it was important to have people close to the site who can go for survey and who know very well the local requirements. In parallel to that, within TotalEnergies, we had the project team and different disciplines in mirror to what we had within Worley. And therefore, the design was done hand in hand together with these two companies to ensure that we satisfy what is required from different levels within the projects. And at the same time, we were in contact with our consortium companies, for example, DBC, who had the important role as a site owner and EPCC manager. Therefore, we had continuous exchange with DBC for that matter. And we had IFPEN and Tsinghua, who were playing the role of technology owner as licensor and as the R&D reference for different questions that we could have within FEED to be answered. And Sintef, who were the general coordinator of the consortium. In the next slide, you can see the scope of the FEED. The central block, which is called S100, section S100, is the reactional section in which we have those reactors like air reactor, fuel reactor, etc., that Vincent showed earlier. This was the main focus of the pre-FEED studies, mainly the PDP process design package was focused on this section. And for the other section, we didn't have a lot of detail. However, in the FEED, what we did was to go beyond this box and cover what is in the ISBL, inside battery limit section. And here, therefore, we covered all of these different sections, going from the air supply, oxygen carrier, and fuel storage and injection into the reaction section, water preparation and steam supply. We had the extraction of solid from the bottom of the reactors, the heat exchangers, flue gas recycling and heat exchangers on the gas phase, and the S800, which is an important section, which is the flue gas management system, which was designed by Dongfang. Therefore, we went beyond the central box and covered all of these different boxes. And at the same time, the interface with the different available utilities on site, which is located in OSPL, knowing that in the next phase in EPC, Dongfang will cover within detailed engineering more details to cover the OSPL for all of these items. Next slide, we can see some of the selected disciplines in terms of engineering design. An important discipline was process design. It is the heart of this. It was the heart of this phase, as the purpose is to demonstrate a novel process. Therefore, it was clear that it is an important discipline. However, it was very challenging because of the fact that it was the first step. Therefore, all other disciplines were relying on that. Therefore, it was important to ensure what we produce is something solid to avoid rework. It was challenging in the sense that we didn't have any reference for this technology. It is first of its kind, even if we had knowledge on fluid catalytic cracking, FCC in refineries, and circulating fluidized bed CFB in the energy production. However, once we were entering to details and some specific questions, there were differences that made it difficult. Therefore, that was one important challenge. Another important point was the very large flexibility required for this plant, knowing that that's a demonstration plant. Therefore, we have quite a wide range of capacity, going from 2 to 4 megawatt thermal. We have variable fuels. For example, we go all the way from biomass to petcoke, which are very different in terms of nature. We have different kinds of oxygen carriers that this plant should be able to operate with, and a lot of other items that doesn't exist for a conventional industrial scale plant, but we should have respected for this demonstration plant. And another important aspect was integration with the what we call backpass system for covering the heat exchange and flue gas treatment. This was designed by DBC based on a conventional design, and it was very compact design as everything is located within a backpass. Therefore, it was important to have a good integration with this section and ensure that everything is working properly. Then we had the system control, which was based on this process design. System control and automatization is important since it permits us to improve the operability and safety of the system. At the same time, we must ensure certain degree of freedom. We shouldn't automatize too much, since then our hands will be closed, and as it is a first of its kinds and demonstration plant, we need certain flexibility. Therefore, this flexibility is very important. It was important to be maintained. A resource that was extremely useful for us for the design of system control was what we had learned from the cold mockups that we had operated in previous years within CHEERS, pilots and models that we had defined within who defined the ranges of the operation for us. Another discipline was instrumentation. A difference with conventional plant here is the fact that the system is extremely instrumented compared to a normal plant, and that's because of this R&D nature. Since we are going to learn, therefore, we have much more instrumentation compared to a conventional plant. And analysis, which is potentially not a big part of the plant, but extremely important for conventional technologies, but extremely important in such a project, as we are going to learn, and our eyes and ears are analyzers. Therefore, it was very important to give a special attention to that. And for instance, it was very difficult to have safe sampling regarding the scale of the plant and its complexity. If we go to next slide, here we can see an overview of the flow of design that we had for process design. We got the conceptual design from PDP, process design package, in pre-FEED phase, and some other items that were coming from that phase. Then we developed a basis. As you can see in this scheme, from top left, we can see the hoppers that are used for injection of the fuel We use a weighting loss hopper, for example, to control the flow of the fuel. We have the oxygen carrier injection, which is for a startup and for the makeup of the oxygen carrier, and it goes to the air reactor, which is the heart of the technology. And we have both air reactor and fuel reactor and carbon stripper that you can see in center of the scheme. We have two separate burners that are used for a startup and shutdown of the plant. Then we have a PU300, that's a package which is there just for safety of the plant in case of some unexpected shutdowns or emergency shutdowns. We have some dedicated systems to ensure safety of the plant. You can see on the bottom the extraction, solid extraction system on the bottom of both air reactor and the fuel reactor, and the compressors which are there for the air and air injection for different purposes. And on the top in green, you see this compact backpass design in which we have the heat exchangers to reduce the temperature of the flue gas. We have the polishing section to ensure safety of the system, the SOx, the NOx, and the dust, and then at the end it goes to the atmosphere. Using this concept, therefore, we developed the heat and material balance for the whole plant for up to 6 cases, 6 different cases. Then we developed the process flow diagrams, which were basis for the piping and instrumentation PNID diagrams. Cause and effect matrix was important, a step to have this control system basis to be developed and be used as the basis for instrumentation, process control philosophy, and different data sheets, etc., that were coming one after the other in the process. And these were the basis for different disciplines that were coming online one after the other. If you go to next slide, here we can see one specificity of our demonstration plant of CHEERS. An important aspect is the fact that we have 2 configurations within one plant. In left-hand side, you can see what we call configuration 1. And in right-hand side, you can see configuration 2. The main difference is located on the carbon stripper technology. In one case, it is on top of the fuel reactor. In the other case, it is just side by side. Another difference is the system which is used for control of solid circulation. In one side, we use L valve mainly for the solid flow rate control, and in the other system, we are using some novel systems of overflow and loop seals to control the solid circulation. This is very challenging. This was very challenging and very promising. It was promising in the sense that it brings a lot of synergy. As you can see, air reactor and fuel reactor are shared, and all of the other sections like air, steam, etc., are shared. However, as the system is very compact, being able to go from one configuration to other is very complex, and we wanted to have something interchangeable in the sense that we can easily go from conf 1 to 2 and vice versa. Therefore, this was done at the end by opening and closing some valves and opening and blocking some pipes within the system. For sure, while the system is in standby, therefore is not operating, we cool it down, we empty the system, and therefore we change from one configuration to the other one. This is an interesting, this first of its kinds, and very interesting since it can show a real synergy and a lot of cost saving for such a demonstrations. Then we have 2 different groups coming together, and therefore putting efforts together and saving a lot of time and money. By doing that, definitely it brings a lot of challenges at the same time. The next slide, we can see an overview of what we had in mechanical design, which was another important aspect of this project. The plant has a quite a small size compared to conventional industrial plant, and this small size brings a lot of limitations. For example, for some pipes, we must respect certain minimum diameter to be sure that we can put the refractory material inside the pipe. Therefore, choosing the good size of the plant to respect these limitations are quite challenging tasks to be done. They have quite limited space within the plant due to the fact that it is small, and at the same time due to a very high level of instrumentation that some parts become a kind of jungle due to the high number of instrumentation within the system and the fact of having two configurations. Therefore, that was a challenging part to be managed within this mechanical design. And for sure, this configuration change is something very important, especially once we have different layers of refractory within the system. Refractory design was critical, we knew that, and to control that, we started already in pre-FEED a study with a specialized institute, which is called ICAR in France, to select the material and do the some tests for erosion and corrosion to select the refractory materials. However, we had some unknowns that we encountered during the FEED, which was interesting. That even if we knew that this is critical, we had some issues there. For example, in right-hand side, you can see two samples for the erosion tests, comparing ilmenite and SiC as the reference based on some conventional tests to measure the erosivity of our material, to select the materials for the erosion resistant layer, especially in the items like cyclone, where we are expecting high level of erosion. Therefore, we gave a special attention to refractory. One of the reasons was this erosion and newness of the system, and at the same time, the autothermicity of the plant during the whole full operation range. Since we have a high surface to volume ratio due to a small size, therefore mastery of the heat loss is very important for the autothermicity to be attained. What we did was a detailed heat transfer calculation covering all parts of the plant, taking into account different ambient conditions, as the plant is located outdoors. Therefore, it was important to take these elements into account. One of the aspects which is related to CLC is the fact that in fuel reactor, we have a reductive environment with high steam partial pressure, which causes some corrosion issues that has to be tackled within this study. And for sure, as I mentioned, the feasibility of installation regarding a small size of plant was an important factor to be considered during the design. In the next slide, we can see an example of the challenges that we faced for the heat loss. Once we entered to the detailed calculations, we saw in some places we don't have enough information. It's difficult to estimate based on the available knowledge. For one of them was the large nozzles. In top parts, you can see a typical nozzle where we can inject some gases or not. And therefore, during the time that there is no injection, we had a lot of doubts about the heat loss within this nozzle. And as we had a lot of them all around the system, a good approximation of its heat loss was very important. As you can see, we selected just one nozzle to be representative of the other nozzles, which, as you can see on the right-hand side, within the plant is quite very small part of the plant. To have a better understanding, we went through a computational fluid dynamics study. What is interesting is that even if for the plant that's a small part, but for CFD that's quite big section. As you can see, the number of mesh goes from 6 to 25 million because of the size. We had a lot of adaptation modifications to ensure that we are selecting the good size. However, that shows importance of the selection of the study case for such questions, since in FEED, once we have such a question, we are talking about 1 or 2 FEED time to answer the question to be in a good range of time. While in R&D, for some questions, we are talking about 6 months. Therefore, adaptation of the size and level of details that we need to simulate was very important to be able to answer the questions on good time. If you go to next slide, We can see, for example, some examples that we have got from this study. As you can see on the right-hand side, we had simulated different refractory layers and the metallic wall layer of the system, the nozzle, the ambient condition, therefore the wind velocity, its temperature, and the temperature inside the unit, different components of the heat transfer like convection, conduction were taken into account, and radiation. And at the end, we obtained the result that we needed, therefore the which was the conduction from the normal parts of the wall, the enhanced conduction via the nozzle, and what we have from the convection of the gas while the nozzle is not in operation. And based on that, therefore, we could narrow our heat loss calculation and ensure that we are within good approximation compared to what we were expecting. If we go to next slide, here I was going to talk about the process safety, which was an important aspect of this study, the HSC overall safety and particularly process safety. As Auling presented, we had started looking at safety from the pre-feed. However, in the feed, we had much more closer look at it. We performed the hazard identification analysis at early phases of the feed, where we had much more details, where we had a qualitative approach to identify overall risks and put some measures and identify them. Then once we had all of the P&IDs ready, we went through a hazard and operability hazard analysis, where we had a systematic approach to go to follow all the pipings and instrumentation within the system to identify and measure and quantify the risks that we could have. And the selected risks went to LOPA, layer of protection analysis, where we paid more attention. We entered in more details to ensure that the risks that are identified with high potential danger are well mastered. If we can eliminate them, or if we need to add some additional protection layers to narrow them to the acceptable level of the consequence. And based on all of them, we developed the safety concept, which will be the basis for the rest of the design of the system. I put two examples of the hazard scenarios. One of them is the mixing of the air coming from the air reactor and the flue gas coming from the fuel reactor in case of incomplete combustion within the fuel reactor at the degraded process condition. This can happen due to many different cases. One example is if we lose the steam generation while we are sending the air in the air reactor, as we don't have a steam, we can form an explosive environment in case of contact, as we have combustible gases. What we did was to define in details the different scenarios that can cause this effect, do some modelings and evaluate the impacts, and therefore well analyze the situation and put proper mitigation measures where required to ensure that the system is safe for such a risk. Another example is rupture of heat exchanger tubes. Different forms of rupture could happen. It can be a small leakage, which doesn't have a lot of impact, or a full rupture of the tubes, which can have significant impact. The problem was that we didn't have we didn't have any veterinary experience on such a condition. Therefore, we needed to go through quite detailed modeling to be able to assess the impact of the such a issue. At the same time, we try to have an inherently safe design that permits to contain everything and reduce the risk of containment due to such risks. What was interesting was the fact that within HAZOP, as we are talking about the circulating fluidized bed system, a cause which was in point A could have an effect in totally different place of the plant. quite far away, as everything is connected due to the solid circulation. And therefore, it took a lot of time to really analyze each scenario and discuss in detail what could happen within the plant. In the next slide, we can see some elements on the constructability. The system is supposed to be built on a brownfield within existing buildings of Dongfang. We adapted the stick-built approach with some prefabrication compared to modular construction strategy, and this will be finalized in EPC phase by Dongfang. There is a large amount of piping due to high level of instrumentation, and the fact that we're nearby the DBC manufacturing site gives us some advantages and some flexibilities. To give some notions, the highest points of the plant is 44-meter high, therefore the plant is quite high, and we have more than 600 tons of the facilities that are supposed to be installed in quite narrow space. Weicheng will show some photos so you can visualize how complex it would be. In the next slide, I would like to therefore do a kind of wrap up and share some learnings. It is divided in two parts. One is in terms of engineering, another one in terms of project management. In terms of engineering, what we can share is the fact that even if such a project is smaller than conventional industrial scale projects in size and budget, but it is more complex in terms of engineering, as it is first of its kind and there is no reference to look at. There are a lot of shutdowns and startups that bring a lot of additional stress, which is not always known for conventional plants. Therefore, it needs to special attention to ensure that the plant will withstand such stresses. Autothermicity, especially in energy generation and combustion for a small scale, is a complex issue due to the high surface to volume ratio. And here we had on top of that two interchangeable configuration, which added a lot of complexities. And therefore, it brings additional challenges compared to a conventional plant. Within FEED, we had some R&D questions, even if we had done an extensive R&D work before FEED and especially for preparation of process design package. And this was very well managed thanks to the high flexibility and reactivity of the R&D teams within TotalEnergies, IFPEN and Tsinghua, and that was very important to have this flexibility and close collaboration together. And what was interesting was the fact that within FEED we could still have some innovative solutions to tackle some issues, and these innovations permitted to reduce the costs, save some times, and improve the process operability and safety. As FEED is still on paper, therefore we can still have innovation and improvement with limited impact on the system. The FEED outcome is definitely important for the pilot plant himself, but at the same time is very important for the next phase, which is industrial scale plant. As here we have a quite detailed design, and therefore it will be used for the techno-economical and evaluation of the industrial scale, what will be done in CHEERS in Work Package 5, and for sure in preparation of the next phase post-CHEERS CLC development. And important challenge here was integration of oil and gas and power standards and European and Chinese norms and regulations, ensuring this safe design. And at the end, we had about 210 deliverables and about 30,000 man hours within this project. And in the last slide, we just give some project management outcome. Agility is very important in such a project due to the fact that we will face a lot of unknowns, and therefore we need to sometimes go back and put on the question some facts and update. Therefore, we need this out-of-box thinking and the fact of being flexible for the design. It was quite short. For example, this FEED was only 9 months. Therefore, we need a fast-track delivery of some items, especially for EPC preparation and long lead items. As Aoling mentioned, we had COVID coming from the beginning. Therefore, all the workshops were done in fully remote. and experienced a lot of complexities and a lot of additional time. For example, for HAZOP, we doubled the time required due to this COVID issue, not only COVID, but also complexity of the plant and what I mentioned, but definitely this had some impact. For example, we didn't have any direct site survey from European side, and everything was done thanks to our link coordination in China and Worley's office in China and DBC. Therefore, this brought some complexities. And at the end, what was important and was always important is intercultural differences and notion of that, having being conscious about that, especially once we are working in remote conditions, since once we are face-to-face, we have a lot of time to know each other better and understand the differences. But once everything is in distance, this hidden part of iceberg becomes bigger. And in CHEERS, thanks to a constructive attitude and exchange environment, we could have a very good working environment and good progress. That's my part, and therefore I leave the floor to Wei-Cheng Li, who will present the EPC preparation. Wei-Cheng, please.
Okay, thank you, Mahdi. So in this section, I will give a brief introduction on the EPC preparation. So after we received the deliveries from FEED, as Mahdi just talked, and from then we start the EPC preparation. So it's about half a year since we received the FEED delivery and start the EPC preparation. So in the next slide, you will see the demonstration unit will be located in Deyang City. So Deyang City is about 60 kilometers on the northeast of Chengdu. As you know, Chengdu is a center city in southwest China, and it's very convenient for international travels. So Deyang City is near Chengdu. It's also very easy to get there to do the test for European partners. And this unit will be located in DBC's test center inside DBC's manufacturing base in Deyang. So in the next slide, you can see the DBC's test center, which is already there with a lot of utility systems can be used for CHEERS demonstration unit. And you can see in this picture, in the left bottom, this corner will be the site for the demonstration unit to be built. And now it is co-shelter. And after the test center phase 2 have been built in 2020, have been finished in 2020. This co-shelter can be removed, and this place can be used for the demonstration unit of CLC. So in the next slide, you can see the existing utility system in the test center, such as electricity, the cooling water system, the chimney, the DCS control room, and the natural gas, compressed air, oxygen, and such utility systems. So most of the utility capacity is enough for the CLC demonstration unit. And also the tie-in point is not far. It's very near to the place of CLC unit. So in the next slide, before EPC, we must get the permission from the local government. And before get the permission from local government, we need to hand the feasibility study report and the environment impact assessment report. We must hand these reports to the local government to get these approvals. So these assessments, these reports are finished in the end of 2020, and after this report received and processed by the local government, so we got the final approval from the local government in April 2021. So in the next page, you can see the final approval from the local government on this project. So the next slide. Yes, this is final approval file from local government. This is a permission for the EPCC project. So so now we have all the all the conditions ready for the EPC project to start. So not only the permission from local government, but also the feed delivery, which is a very important input, and this is a very good foundation for EPC project to start. And as you can see from Marty's presentation and also Olin's introduction, this FEED work package is very difficult, and under the efforts from Total and also the Worley Design Institute, this work have been done very good and delivered to DBC in the middle of 2021. So after we received the FEED deliveries in this half year, we did a lot of work on the preparation on the EPC project. So by now we have almost finished all the detailed engineering, and also started some purchasement for long lead items, and the construction is under call for bidding. And this whole EPCC project is expected to be finished in this year, 2022, and then from 2023 we will start the test of the research. So in the next slides, you can see to ensure high efficiency conducting of the EPCC project, we need a very good work structure, the management structure. And from our experience, previously we did some MWth combustion test facility. So from the experience we gained from previous projects, we have a work structure, a management structure to ensure the project goes well, goes efficiently, and make the project progress as expected. So firstly, we need a leading team with DBC's vice president as the leader, and also the directors from relevant departments as leading team members. This is a good way to make the resources need of the project can be guaranteed. And also, we have already hold the kickoff meeting, and this kickoff meeting is finished in December 2021, and now the EPC project have actually started. And under the leading team's supervision, we have a working team, and I will be the coordinator of the working team. And under working team, we have different teams, such as the engineering team, the purchasing team, the construction management team, and also the commissioning team. So each working team, each special team, we have one team leader and with members from the relevant special disciplines from different departments. And this is a working structure. And in the next slides, this is a work breakdown of this EPCC project. Means the subcontracts of this EPCC project. So now the civil contract have been signed 2 or 3 months ago, and the civil work have started today. And also the long lead items, this contract have been signed 2 months ago, and also the contractor have started the purchasement of the material, and the preparation for the manufacturing is under work by the contractor. Also, the electricity and the control system, we will have a small EPC project for this system, and the contractor have been selected. They will be responsible for the detailed design and also the purchasement of the devices for the electricity and the control system. And also some fans, the key equipments will be purchased by DBC, and this work are under call for bidding now. And also the steel structure manufacturing and installation, together with equipment installation, this work are as one package to minimize the interfaces and to make the construction process more efficient. So this work package is also under call for bidding now. So after this is commissioning, and the commissioning will lead by DBC's commissioning team for CFB boiler. So this is work breakdown now. And in the last page, is the last page. This is the latest news. Yes, this is only 2 or 3 hours before now. In this afternoon, we have started the destruction of the existing coal shelter on the site, and this work will be finished before Chinese festival, Chinese Spring Festival, and the civil work will be started after the Chinese Spring Festival. So this is this section on EPCC preparation. So thank you, and I will give time to Vincent, I think. Yes.
Thank you very much, Wei-Chen, for this good news on this project. As part of Work Package 4, I will finish the webinar with a CO2 treatment study, which is part of this Work Package 4, and that will be used for the Work Package 5 into the technical economic assessment. So here in this section, we are more talking about industrial scale units, real one. So as you can see, in a CLC unit, you have the combustion section, but you have also two other blocks, which will be the fuel gas treatment and compression, and you have also the power generation. So this part will mainly speak about the fuel gas treatment. In fact, you may have different CO2 quality because you may have different fuel feedstock. You can have petcoke, you can have coal, lignite, biomass, waste, gas. This will give different quality of fuel gas, of CO2. And then you have, for sure, the destination of the CO2. What will you use it for storage, utilization, transport, how you transport it, by ship, by pipe. And in this study, the quality which was chosen was the EOR quality, the enhanced oil recovery quality when the CO2 is re-injected in well. The specificity for CLC, if you compare to other combustion technology, is that, in fact, you have no nitrogen, no dilution of the flue gas. So you have a kind of flue gas which is very concentrated. If you have pollution or contaminant, it's very, very concentrated. And here we took the worst case scenario, which was the petcoke feed, because in this feed you can have sulfur in high quantity and nitrogen as well. So we did a study with a technology provider named IFPEN, and in this study we discovered that we needed to have a DNOx to reduce the NOx, a DDust to take off the particles, and a DSOx to remove the SOx. And after that, you will have the compression section and the drying part to be able to transport or to put the CO2 in a safe place. So this is not a negligible part, because it has really been to be taken into account at the start of a project to know what you will have to do with the CO2 downstream the CLC unit. On the air reactor side, the nitrogen will probably only go through a DDust or an ESP to be safely released in the atmosphere. But all this equipment are needed on the reactor side, fuel reactor side. So if we speak about the first block, it will reduce the NOx. Just to mention that all these blocks are the temperature of the process will be important for each step. So with IFPEN, technology provider, we discuss many scenarios on how to organize these three blocks, the DNOx, the DDust, and the DSOx. And we looked at different possibilities, having some recycled fuel gas and putting some exchanger in different places to know how to control the temperature in between these different blocks. For the first block, the selective catalytic reduction was chosen for the DNOx. Basically, quickly, in this technology, you will mix ammonia and oxygen in the flue gas. And when it's mixed, it will go on a catalyst where some oxidation will happen. Why did we choose this technology for the DNOx of the CLC? And this technology can handle a quite high amount of NOx, and this is why it has been chosen. And it also can handle quite a high dust load. In fact, as you are above the DDust, you have a kind of high amount of dust. And this technology allows to have a kind of, you can choose the size, in fact, the pitch of the catalyst. And you will have a very big section to be able to handle this amount of dust. The temperature, as I already told, is also an important parameter, because you need to be below 450 degrees for ammonia stability, but you need also to be above 200 to to prevent harmonious salt formation. And this reaction is also exothermic, and then you can recover some heat again. So this will be combined with another study for heat, maximum heat integration and recovery in the unit. The second step is the dedust. You need to remove the particles before letting the CO2 going out. So for this technology, we choose an ESP, or electrostatic precipitator. Basically, you will implement a very high voltage between a discharge wired and collecting plate. In fact, the flue gas, which is loaded with particles, is being ionized, and these negative ions are attracted to the plate, the positive plate. On their way, these ions are collide with particles, and they bring the particle to the collecting plates. And then at certain times, you will with wrapping device, you will let the cake formed on the plate going down on hoppers below. And why did we choose this ESP technology? So it is used mainly in CFB and FCC technology. But this can handle different type of particles. In CLC, we have 3 types of particles to handle. We have the ashes to tackle, the oxygen carrier particles, and the unburned char. And for the performance of this ESP will depend on the diameter of the particle and some electric resistivity as well. So moisture and temperature is important as well. That's why also we need to control temperature before the ESP as well. The last one is the fuel gas desulfurization to remove the SOx. And for this technology, we use an in 2-step desulfurization unit, which is with an absorbing tower by letting a scrubbing liquid going through the sulfur dioxide, and bring this liquid into a reactor tank where you do the oxidation and neutralization of some dioxide bisulfite, and you transform that into gypsum. Why did we choose this technology, the wet fuel gas desulfurization? Because this technology can again handle high amount of SOx. Sorry, as I told you, for petcoke, which is the worst feed, where you have lots of sulfur and you need to handle quite a big amount of SOx. And we choose non-regenerative one-through technology, which has a very good efficiency. Even to increase this efficiency, we can use lime instead of limestone. And we will clearly study the spray nozzle distribution. How do you use it, countercurrent, co-current? This will be also studied carefully to have maximum contact. And it was chosen as well to have the regeneration section separated from the absorbent tower, to not to have some air ingress into the flue gas. So as a conclusion, you see that after the CLC combustion, you really have to take care about what the destination of this CO2, how you will transport it, how you will store it, what you will use for, so that you can design the CO2 conditioning unit behind. And all this study will be sure used in the work package 5 when we will do the TEA, technical economic assessment, on a 525 megawatt thermal unit. So as a conclusion, we went through a very good adventure on doing this feed for the CLC. We face up many challenges, how to ensure the optimal integration into the DBC site. The grassroots solution was chosen. In the feed, we went to many details, and we deliver more than 300 deliverables in this feed to pass this to DBC for the EPC. As you've just seen, Wei-Chen told that the EPC just started and is well launched. And we have also seen how to handle the CO2 conditioning to start the industrial part of this CLC. So all these tasks were possible because of these many meetings, many in English and sometimes in Chinese, between Europe people and Chinese people. And this can be done with this wonderful collaboration in this project. So the next perspective, the next step, as we say, is the EPC now after the work package 4, and it's just started. And it should last, as Wei-Chen said, 1 year, and we'll dedicate the 2023 for testers. Just a quick look on the 2 other work package. So work package 3 on the oxygen carrier development. So it's finished as well, and the selection is of the ilmenite-based oxygen carrier is done. There will be a webinar on the 26th January on this subject. And the other work package is the work package 5, which is really started, and we are in the process of providing first estimation cost on the TEA will be delivered in February this year. So thank you very much for your attention. And we are here to answer any question if you have. So please use the Q&A, please, if you want to ask any question. Thanks a lot.
Okay, that was a very detailed and illustrative summary of the results. Thank you, all of the presenters and panelists. We have not received any questions, so that must mean our audience is very expert, or that maybe they've been working on these this project itself. So once again, I thank you all for attending, and remind you that we have a work package 3 webinar on the 26th, as Vincent noted, and the registration went out with the same registration for this webinar, but we will send reminders tomorrow. Once again, thank you for attending, and this recording will be published on our YouTube site. So still no questions. So I propose that we conclude and wish you all a great day, either the evening or the rest of the afternoon, and hope to see you in the next webinar.
Thank you. Bye.
Thank you. Goodbye.
Bye-bye.
Thank you.